last class we discussed about optical joint density of states rho of nu and the probability of emission Fe of nu or Pe of nu and probability of absorption Fa of nu. We wanted to find out the number of emission. Finally, our objective is today in this class we will discuss about rates of emission and absorption, and our objective is rates of emission and absorption refers to number of emissions or absorptions per unit volume of the material per unit time. Because once we know this number, then multiplied by h nu will give us the power, energy per unit time gives us the power output from this device or material. So, the number of unit emissions per unit volume, this is the density of optical joint density of states, that is number of states available for photons of frequency nu to interact with. So, rho nu is the number of states. This is the emission probability, and therefore, number of states multiplied by the emission probability will give you number of emissions. So, rho of nu into Fe of nu will give you number of emissions per unit volume, because this is per unit volume, and therefore, the rate of spontaneous emission, rate of emission or spontaneous emission RSP is proportional to rho of nu into Fe of nu, or RSP, SP standing for spontaneous emission. Why it is spontaneous emission? I will come in a minute. So, this I can write as equal to a rate constant A into rho of nu into Fe of nu. A is the rate constant, and you can show that this is nothing but 1 over tau r, where tau r is the radiative recombination lifetime. So, this is the radiative recombination time or recombination time for radiative transitions, recombination time, radiative recombination time means recombination time for radiative transitions. Why I mean radiative transitions is the following. If you see the EK diagram, as you can see, I keep drawing this many times. So, EK diagram, a photon, an electron which is in the conduction band can make a downward transition in energy to the valence band, giving out spontaneously on its own a photon of energy h nu. It is also possible that this recombination may not result in the emission of a photon at all. This recombination is also possible through phonon emissions. Vertical transitions are also possible with phonon emissions, and therefore, in general, or this may be sitting here, it makes an oblique transition, but the point is a transition from conduction band to valence band may take place with emission of a photon or without emission of a photon. Therefore, total number of spontaneous downward transitions comprise of radiative plus non-radiative transition. So, radiative plus non-radiative transition. So, total number here, total number of spontaneous transitions, spontaneous because it is on its own, it is coming down. Spontaneous transitions would comprise of radiative and non-radiative components, and therefore, correspondingly the total rate constant, if I denote it as T, then this will comprise of a radiative constant A plus a non-radiative constant which I denote as S. Total rate constant equal to radiative constant plus non-radiative constant here. The rate constant, therefore, this is inverse of time, it is rate constant, therefore, it is inverse of time. So, this is written as 1 over tau r plus 1 over tau n r. In other words, T is equal to 1 divided by tau is equal to 1 divided by tau r plus 1 divided by tau n r, where tau is the lifetime of the transition or recombination time, spontaneous recombination time. So, this is recombination time. This is radiative recombination time, this is non-radiative recombination time. The relation is 1 over tau equal to 1 over tau r plus 1 over tau n r. We will discuss about this a little bit more a little later, but at this point I will just make a statement that in direct band gap semiconductors, tau r is of the same order as tau n r, which means the rate constant A is of the same order as the rate constant S, which means the spontaneous emissions, this is spontaneous emission, rate of spontaneous emission of photons, RSP of nu, of frequency nu. If this is equal to this, it means out of the total recombinations, 50% of them result in emission of photon and 50% of them result in emission of no photon, that is no emission of photons. If A equal to S, if tau r equal to tau n r, it means that A equal to S, total rate constant is this, which comprises of these two, radiative, non-radiative. Therefore, in a direct band gap semiconductor, the probability of radiative transitions is equal to, nearly equal to probability of non-radiative transitions. Almost every electron combining with a hole, 50% probability of emission of a photon and 50% probability of no emission of photon. But in the case of indirect band semiconductors, tau n r is much smaller than tau r, and therefore, S is much greater compared to A. We will put some numbers a little later when we go to materials. Therefore, non-radiative transitions dominate much more over radiative transitions. It is that is the importance of tau r and tau n r. So, I want to bring at this stage an analogy with atomic systems, because most of you would have elementary theory of lasers, most of you are familiar with the elementary theory of lasers. You will see that there is a complete one-to-one analogy, and then I would like to proceed further. See, atomic system, if you consider a two-level atomic system with n1 number of atoms in the ground state and n2 number of atoms in the excited state, with energy E1 and energy E2 and energy E1. Then there are number of atoms, large number of atoms in the ground state, which is given by the Boltzmann distribution. There are fewer number of atoms here. The three basic atomic processes are the same interaction processes. An atom sitting here can make spontaneously a downward transition, giving out an emission of photon h nu. The number of transitions, N2 is the number of atoms per unit volume of the material. The number of transitions, downward transitions, spontaneous transitions, is proportional to the number of atoms which are sitting here, and therefore, the rate of transition, spontaneous transitions is proportional to, if I am looking at spontaneous emissions, then this is proportional to N2, or rate of spontaneous emission is equal to A times N2. There can be stimulated emission in the presence of photons of energy h nu if there is a energy density u nu of photons of energy h nu. U nu is the energy density, which means number of photons per unit volume of frequency nu. That is, if you have n number of photons incident, then n h nu divided by volume of the material V is u nu. So, this is equal to u nu, energy density. So, if u nu is the energy density, then rate of stimulated emission is equal to a constant B into N2 into u nu, and rate of absorption is proportional to the number of atoms in the ground state, and therefore, rate of absorption is equal to B into N1 into u nu. Please see, when there is an energy density, when there are photons of energy h nu here, they can stimulate downward transition, but they can also cause absorption, upward transition. So, the absorption depends on the energy density u nu and the number of atoms in the ground state. Emission depends on the number of atoms N2 here, but also on the energy density u nu. That is why we have this kind of expression. To make it, to incorporate more features into this, actually atom interacts with radiation over a certain range of frequencies. So, there is a line shape function G nu, atomic line shape function. Those of you who have studied basic laser physics, line shape function. If you have not studied, does not matter, G nu, and therefore, everywhere this RSP will be a function of nu and N2 into G nu. G nu gives us the strength of interaction at the frequency nu. That is, any atomic system interacts with radiation over a range of frequencies, because of various mechanisms which are called line broadening mechanisms. This G nu is the line shape function which determines the strength of interaction at a particular frequency. So, everywhere you will have an additional term G nu, that is N2 into G nu, N1 into G nu. So, spontaneous emission at a frequency nu is proportional to N2 into G nu, and A is the proportionality constant. So, these are the three expressions that we have. For a non-degenerate system, this for absorption and emission B is the same. Otherwise, you have to write here B21 and B12. For a non-degenerate system, it is the same. And these coefficients A and B are called, what are they known as? These are known as the Einstein coefficient. So, A comma B are the Einstein coefficients. A is equal to 1 over TSP, where TSP is the spontaneous emission lifetime. You can write this as dN2 by dt equal to minus AN2 into G nu, and simplify, and you can show that A is equal to 1 over TSP, where TSP is the spontaneous emission lifetime. In atomic physics also there is a relation, that is lifetime tau is equal to 1 over TSP plus 1 over TNR, non-radiative transitions. So, TSP here refers to spontaneous emission, but also there can be an atom may come down without even giving a photon, and they are called non-radiative transitions. So, it is the same relation that we have in a semiconductor, that 1 over tau lifetime is equal to 1 over radiative lifetime plus 1 over non-radiative lifetime. So, A is given by 1 over TSP, this is called spontaneous emission lifetime, and the relation between A and B, relation between the Einstein coefficients is given by A by B is equal to 8 pi h nu cube divided by c cube, or in a medium of refractive index n, it is c by n cube. This is the relation between the Einstein coefficients A and B, and A is equal to 1 over TSP. Why I am writing this is because the coefficients that we have in semiconductor A and B also have the same relation. So, the rate of, therefore, this I have written for the atomic system, and now I write for the semiconductors, and then you can see what is the comparison from here in an atomic system and in semiconductors. Here we are writing N1, N2 are number of atoms, here we are dealing with electrons and holes, but you see the similarity and the relations. So, for semiconductors, RSP of nu is equal to the constant A into rho of nu into Fe of nu. This is spontaneous emission. Stimulated emission, RST of nu is equal to constant B. Actually, it is A dash and B dash, because the numerical value is not the same, but the relation is the same. So, B into rho of nu into Fe of nu into energy density U of nu, and R absorption of nu is equal to B into rho of nu, and now F A of nu into, and A and B have the same relation here. In this case, A is the spontaneous emission lifetime, here A with A is equal to 1 over tau r, radiative recombination lifetime. There are techniques to, these are measurable parameters. You will see ultimately that everything will be in terms of lifetimes, because lifetime is a measurable parameter. If time permits, later on I will discuss the measurement technique, how one can measure the lifetime. So, A is equal to, it is completely one-to-one correspondence, and what do you see, that if you replace N2 into G nu, this tells you effective number of atoms available for the transition, and this tells you the same thing. So, it is rho nu into Fe of nu is replaced by this, otherwise it is the same. So, these are the rate of spontaneous emission, stimulated emission and absorption. The difference between stimulated and spontaneous is the energy density. Spontaneous emission does not require any radiation to be present, it spontaneously makes a downward transition. In stimulated emission, you need radiation to be present, and therefore, U nu here refers to the density of states. So, U nu here refers to the energy density in the medium. So, in stimulated emission, if I want to illustrate stimulated emission, then I have photons coming here of energy density U nu, and electron which is here making a downward transition and leads to. So, if there are more number of photons coming here, it can induce more number of downward transitions. That is why stimulated emission rate is proportional to U of nu. Larger the number of photons which are incident here, larger will be the possibility of stimulated emission, and the coefficient here is B. So, these are the Einstein coefficients They are the same as this, not in magnitude, but in nature, and the relation is the same in semiconductors. So, let us find out first the rate of spontaneous emission. First we will discuss spontaneous emission, because as I have already mentioned, spontaneous emission is the basis of operation of LEDs. So, we will discuss the rate of spontaneous emission. We will find out what is this rate. We have written an expression here, but let us see what is that rate. So, rate of spontaneous emission RSP at the frequency nu, because the density, optical joint density depends on the frequency nu. RSP of nu is equal to 1 divided by tau r into rho of nu, density, optical joint density of states, 1 divided by pi h cross square into twice m r to the power 3 by 2, please check the expression, into h nu minus E g to the power half. So, this is rho of nu. So, A, this is rho of nu multiplied by F E of nu, probability of emission. Let us see the probability of emission. F E of nu is equal to, if you recall, first at thermal equilibrium, let us see at thermal equilibrium. At thermal equilibrium, I want to find out F E of nu. So, we have a semiconductor, the Fermi level is somewhere, I do not know p type or n type. I am just taking a semiconductor, not taking a p-n junction yet, and this is E c, a semiconductor in thermal equilibrium. F E of nu is equal to F of E2, that is probability of having an electron at state E2, into probability of having a hole at state E1, 1 minus F of E1. So, substitute F E2 is 1 divided by 1 plus e to the power E minus EF. So, E2 minus EF by k. Into this one will give me e to the power E1 minus EF by kT in the numerator, divided by 1 plus e to the power E1 minus EF by kT. Let us approximate a little bit. EF is here, E1, remember that E2 is a energy level here in the conduction, in the valence band, in the conduction band. So, E2 is an energy level in the conduction band, E1 is an energy level in the valence band here. So, you can see that this gap, that is E2 minus EF, is much greater than kT at room temperature. This is the Boltzmann approximation. E2 minus EF is much greater than kT, because kT is about 0.025 eV. Therefore, just like we did Boltzmann approximation for carrier concentration, under the Boltzmann approximation E2 minus EF is much greater than kT. Therefore, the exponent is a very large number. So, I can neglect 1 with respect to e to the power large exponent, which means this second term here is first term here, the first term, this one is simply approximately, let me write approximately. I want to see what kind of numbers are there, approximately equal to e to the power. So, only this one, now it is minus, goes to the numerator, E2 minus EF by kT. The second term here is approximately equal to e to the power E2 minus EF by kT. What about this term? This is a large number, E1 minus EF by kT is a large number. So, you can neglect, but it is a large number, but E1 is less than EF. Please see, E1 is here, EF is here. So, E1 minus EF is a negative number. So, it is a large but negative number, therefore, this is close to 0, and therefore, I can write this term is close to 0. So, I neglect this. So, what we are left with is only e to the power E1 minus EF by kT. And what is that? You see, plus EF and minus EF by kT, that goes off. So, you are left with e to the power of minus E2 minus E1. So, this is, therefore, this is approximately equal to e to the power minus E2 minus E1 by kT. E2 minus E1 is what? H nu. So, this is equal to, okay, let me erase this. So, what we have got is F e of nu is equal to e to the power, I should not have erased e to the power minus, let me write again, E2 minus EF by kT into e to the power E1 minus EF by kT, which is equal to Fe, this term is approximately equal to, because I have made Boltzmann approximation here, this is equal to EF goes, and we have e to the power minus h nu by kT. So, F e of nu is e to the power minus h nu by kT. You can put some number. If you are talking of visible photons corresponding to visible light, h nu is about 1.5 or 2 eV, and kT is extremely small compared to that. Therefore, this is a very large number, e to the power minus this. So, F e of nu is an extremely small number, probability of emission at thermal equilibrium is extremely small. Suppose I was in quasi equilibrium, we were in a state of quasi equilibrium. So, we will substitute this here in a minute, but just before I proceed, suppose we were in quasi equilibrium, which means let us say we have pumped. So, this was our original EF, we excite this medium by maybe by illumination, maybe by current injection, whatever reason, so that the EFs separate out, 2 EFs come. Now, so we have one EF for the conduction band EFC and one EF for the valence band. So, EFV. So, I erase this thermal equilibrium case. So, this was thermal equilibrium. Now, this is in quasi equilibrium. So, what difference would we see? Please see, I have, it is not large enough that EF and EC have merged here. Still this gap is sufficiently large between E1 and EF, so that I can still apply Boltzmann approximation. Assume that I am still able to apply Boltzmann approximation. So, what difference in this expression will come? In this we will have EFC and here we have EFV, that is the only difference. EFC, E2 minus EFC by kT, and E1 minus EFV by kT. Please write this expression again. What do we then have? Earlier EF was, they cancelled each other. Now we have this multiplied by e to the power EFC minus EFV by kT. So, the probability of emission in quasi equilibrium has changed to this expression, where this was in thermal equilibrium, that is now multiplied by a term EFC minus EFV by kT. See in this diagram that I have drawn, EFC minus EFV is this gap. It is much larger compared to kT, 0.025 eV, and therefore, this exponent here is a very large number now. This is very large, no doubt, but this is also large. The point is, by pushing the semiconductor into quasi equilibrium, you have additional multiplication factor, which will increase Fe of nu by orders of magnitude. A semiconductor in thermal equilibrium had Fe of nu approximately equal to e to the power minus h nu by kT, which means the probability was very small. By pushing the semiconductor into quasi equilibrium, maybe by injection of carriers, maybe by illumination, different means, you have an additional factor which is also a very large factor. In other words, you can change the probability of emission by orders of magnitude. We will see this implication later. That is how in an LED before bias, there is nothing, zero output. You just forward bias it, light starts coming out. What are you doing by forward biasing? You are simply raising the probability of emission. All right, we will discuss more about this a little later. So, let me continue with the thermal equilibrium case. So, I erase this. So, in thermal equilibrium, the rate of spontaneous emission is given by, so we have the expression here, Fe of nu is, please write, you could write this again, e to the power minus h nu by kT. Fe of nu is replaced by e to the power minus h nu by kT. We want to simplify this to a form. If you multiply this expression by e to the power Eg by kT and e to the power minus Eg by kT, e to the power Eg by kT and e to the power of minus Eg by kT. So, RSP is equal to 1 over tau r 1 over pi h cross square twice m r to the power 3 by 2 e to the power Eg by kT into h nu minus Eg to the power half. I have simply multiplied by e to the power Eg by kT and e to the power minus Eg by kT, e to the power h nu minus Eg by kT. E to the power minus Eg by kT is here and e to the power Eg by kT is here. Is just to write it in the form of x to the power. So, this, therefore, this constant here, if we call it as some constant d or d0, then this into h nu minus Eg to the power half into e to the power h nu, oh this is minus e to the power minus h nu by kT, in which case, so this minus minus plus, so I should have minus here. Please correct it. So, e to the power minus h nu minus E g, because h nu is greater than E g, therefore, minus h nu minus E. So, please correct this. So, this is of the form some constant d 0 into x to the power half into e to the power minus a x, where a is some constant, a or p, let me write p, because a we have used for lattice constant. So, e to the power minus p x, where p is equal to 1 by k t. Is that okay? This is of the form x to the power half, that is x is h nu minus E g, I am calling as x to the power half into e to the power minus p x, where p is 1 by k t. So, this is the rate of spontaneous emission. I want to see what kind of variation that I will get, that is why I have written it in that form. So, how does this vary? We want to find out rate of spontaneous emission. So, this is h nu, photon energy h nu, and here I am plotting R S P of nu. So, where will it start? H nu equal to E g, because all density of states, everything is valid for h nu greater than E g. So, this is E g, h nu equal to E g is x equal to 0. So, from here as h nu increases, this goes as x to the power half. So, x to the power half variation goes like this, x to the power half variation. E to the power minus p x variation is exponential drop. Okay. So, e power minus p x at x equal to 0, it has the value 1 at x equal to 0, and then it drops down rapidly. So, it is an exponential drop depending on the value of p. If p is very large, as you can see here, it is a large quantity, 1 by k t, k t is 0.025, that means 1 by 0.025, 40. So, p is about 40. So, it is dropping like this. So, this is e power minus p x variation, and this is x power half variation, and d 0 is a constant. So, d 0 does not involve nu, so it is a constant. So, how would the net result look like? So, the net result would look like initially this function is very, so it is a product of functions, product of two functions. So, the product is 0 here, but suddenly this is a large value. So, the product jumps, it goes up to some maximum, because later on exponential takes over. Please remember that x power half, oh I am sorry, why did I write x power minus half, x power half, please correct this, x power half. X power half is a much slower variation, exponential dependence is much faster. So, exponential takes over and then the net drops down. So, what have I plotted is rate of spontaneous emission as a function of h nu, which means it is maximum at some value here. So, R S P max corresponds to some value here. So, this is R S P max, and it also has a certain line width, line width in the sense where f w h m, from here if you come down to half its value, approximately half its value. So, this is delta lambda. it is delta H nu here in this case, but you can find out what is the corresponding. So, in this case it is delta H nu. The full width at half maximum gives you the line width of this source, full width at half maximum. How do we find out what is the maximum, where does the maximum occur? We have an expression here for RSP nu is equal to D0, it does not have nu, H nu minus Eg here to the power half into this. We want to find out the maxima. How to find out the maxima? So, how do we find the maxima? You differentiate this function with respect to H nu and find out where is the maxima. So, please do this as an exercise and see where do you get this maxima. This maxima corresponds to Eg plus half kT. Please show this, that the maxima appears at Eg plus half. Do this as an exercise. And once you know that the maxima is at Eg plus half kT, simply substitute Eg plus half kT here and you get what is the maximum value. RSP of nu, if you know that it occurs, the maxima occurs at Eg plus half kT, substitute this value for H nu. So, Eg goes away, you are left with half kT to the power half and here again half kT. So, kT cancels, see what you get. So, you know what is the maximum value here, and we know every parameter in this. For a given material we know radiative recombination lifetime, constant, the reduced mass, all parameters are known. So, at a given temperature you know what is D0 and therefore, you can find out what is the maximum rate of spontaneous emission. Remember that rate of spontaneous emission is number of emissions per unit time per unit volume. If you multiply this by the energy of the photon H nu, it will give you power output from that material, power per unit volume. One other thing, that note that the D0, all right, let me write twice mr 1 divided by pi h cross square. What else did I have? 1 over tau r. The D0 value of D0 tells you how far it goes. It is an amplitude multiplying constant here. So, whether this variation goes like this, whether this variation does like this is determined by D0. And what is determined by, what determines D0? D0 is determined by temperature. All are constants for a given material. So, two things, one is tau r, radiative recombination time, and here T. So, larger, if the temperature is larger, then this exponential negative quantity becomes smaller and therefore, D0 will be higher. So, it is instructive to see that you put different temperatures. For example, you put 250 K here, 300 K, 350 K, you see that it changes. Similarly, when you put T different values, the peak shifts, because this is Eg plus half kT. Larger kT means the peak shifts. So, deliberately I have shown the peak shifting slightly, see. So, this peak shifting, because higher temperature will have larger spontaneous emission coming out and also the peak shifted by a small value. So, this tells us the rate of spontaneous emission, from which we can calculate the spontaneously emitted power at any frequency greater than Eg. So, please do this as an exercise to find out the h nu corresponding to the peak value and this one corresponding to the full width at half maximum. So, you can show that in terms of lambda, delta lambda I think is nearly equal to 1.45 into kT. Delta lambda comes out to be, I think it is 1.45 into kT multiplied by lambda p square. So, two exercises, please work this out. Delta lambda is equal to, so delta lambda here refers to, so let me just explain this how you would go about it and then I will stop. So, first for a given temperature find out this. So, you know Eg plus half kT, half kT. Substituting this value, you know what is the maximum value, RSP max. So, this is max. So, where RSP max becomes half, so this is the value where this is RSP max by 2. There are two values of h nu and hence nu. You will get two different values for which you will have the value RSP max by 2 at two different h nu values. So, correspondingly you will get two frequencies, one here for nu 1 and one here nu 2, h nu 1 and h nu 2. So, you know nu 1 and nu 2. If you know nu 1 and nu 2, you can find out what is lambda 1 and lambda 2. Simply C by nu 1 and C by nu 2, and therefore, delta lambda is equal to lambda 2 minus lambda 1. Why we want in delta lambda is normally the line width of a source is expressed in terms of nanometers wavelength delta lambda. You may have heard or studied that an LED has a line width delta lambda equal to 20 nanometers. What have I plotted? I have plotted intensity output I lambda as a function of lambda. Optical measurements are done at wavelength. So, you change the wavelength and measure the spectrum of an LED output and you have intensity variation as a function of lambda. The full width at half maximum is delta lambda, which is typically 20 to 30 nanometer for a light emitting diode. If you measure the same thing for a laser diode, normal laser diode, this delta lambda will be of the order of 2 to 3 nanometer for laser diodes. For normal laser diodes, Fabry-Perot laser diodes. We will study about specialized laser diodes, special laser diodes which have extremely small delta lambda, single frequency laser diodes. So, that is why please calculate delta lambda in terms of nanometers. Lambda p here corresponds to the peak wavelength here, that is lambda p. All right. So, I will stop here, and in the next class we will discuss about rates of stimulated emission and absorption and see the condition for gain, under what condition we can have gain from the semiconductor. Spontaneous emission, there is no gain, but you have an emission spectrum, but stimulated emission can lead to gain under certain circumstances, certain conditions, and we will see that under what condition we will get gain.